Hello everyone, my name is Bo Qian from the University of New South Wales here in Sydney, Australia. Today I'm presenting our joint work influence robustness of multiplex networks against attacks. We'll begin by providing background information. The robustness of a complex network reflects on how easily its structure will break down when nodes of high influence are removed. Retaining the overall robustness when the important nodes are removed is essential to maintain the network communication efficiency. For example, if a house is linked to only one electricity substation, then this station is a single point of failure, because if it breaks down, the house has no other sources of electricity. The problem we have identified is that extensive analysis has been done on single-layer networks, but not much has been done on multiplex networks. So in this paper, we focus on filling this gap by first proposing a new multiplex network centrality measure, then evaluating its effectiveness by comparing with existing measures. In an associative network, when influential nodes are removed, the structures remain the same. Whereas in disassociative networks, when influential nodes are removed, the structure tends to break down easily. A multiplex network is a type of complex network with multiple types of connections between the exact same set of nodes. It has a wide range of applications of modeling real-life interactions, including neuroscience, social networks, critical infrastructure, and economics. We'll continue using the multiplex networks G on the screen as the example throughout this presentation. From the basic definition of multiplex networks, we give the definition of K-core per location. K-core per location is defined as the maximal subgraph where each node has at least K edges of each layer. K is known as a core vector. For example, the 0,0 core is the set of nodes with at least 0 edges on both layers. We see that 0,0 core is the original network. The 2,0 core is the set of nodes with at least 2 edges in layer 1 and at least 0 edge in layer 2. We see that node A is no longer in the 2,0 core because it doesn't satisfy this definition, so on and so forth. Then from the K-core per location definition, Gallimberti proposed the core containment relationship between cores. Informally, we say K prime contains K if all elements in K prime are less than or equal to its corresponding element in K. From there, the containment relationship can be visualized as a tree-like structure known as the core lattice. In the core lattice, cores in higher levels must contain cores in lower levels if there exists a path between the two cores. The core lattice can be constructed from the original network by iteratively removing nodes. We now give background information about centrality measures and attack methods. The two common types of attack methods are random attacks and targeted attacks. In targeted attacks, important nodes are identified and ranked through a centrality measure. To identify influential nodes on a multiplex network, one can extend from monoplex network centrality measures. We denote these methods as classical approaches. These methods usually either project the edges in all layers onto one single layer before applying a classical centrality measure, or they take an average influence of each node on different layers. Recently, novel approaches have been proposed by using random walks, gravity models, or posteriori measures. Our new centrality measure, denoted as multi-core rank, is based on two key observations from the core lattice. First, we observe that nodes on lower levels of the lattice are more connected than upper levels on all layers. Second, we observe that on the same core lattice level, nodes that appear more often have a higher chance of being a child core on the level below. Now, considering observation 1, for an arbitrary level L, we assign a weight L, allowing nodes at deeper lattice level to have a larger weight. Next, considering observation 2, for an arbitrary node V, if V appears on both level L and L plus 1 on the lattice, we aggregate V's influence from all the cores that contain node V on level L as its influence on level L plus 1. This can be thought of as a message passing based inference calculation. In this way, nodes with more appearances will be assigned a higher influence than those with fewer appearances. Before providing the formal definition of multi-core rank, we first define a father-children relationship, where a core K on level L is a father of a core K prime on level L plus 1 if there exists a direct edge between the two cores. The following formula gives the detailed calculation of the multi-core rank influence of a node V on level L plus 1 of a core lattice. To illustrate our method, consider node A. At level 0 of the lattice, since the 0,0 core contains the entire network, we initialize all node influence to 1. On level 1, first we find the 1, 0 and the 0, 1 cores which contain node A. Next, for each of these cores, we multiply layer weight by the influence of A in its father core and the number of fathers this core has. Then we find the influence of A in layer 1 by summing A's influence in cores that contains it. On layer 2, the same algorithm is applied again, and the rest can be calculated accordingly. For our empirical analysis, we use the average layer-to-layer degree correlation proposed by Nicosia in 2015 to measure network assortativity. For the dataset, we used open source undirected multiplex networks. We found that our method correlates the most with overlapping degree. This is justifiable since K-core is obtained by removing nodes that no longer satisfy the degrees given by a coordinates vector, leaving only the nodes with higher degrees. Hence, our method is also based on the degree of a node. In addition, we compare the effectiveness of our method when random and influential nodes are removed from the network. In general, the quality of our centrality measure is demonstrated through the sharp decrease in the number of cores at the beginning of the attack. Comparing with associative networks, neutral and disassociative networks break down quickly when nodes of higher influence are removed, which is as expected. Continuing on the node removal experiment from the previous slide, we also analyzed the impact of overall network associativity when nodes are removed. We've shown that the associative networks remain relatively associative after node removal. The disassociative networks remained disassociative. The neutral networks remain neutral. However, there is a trend in decreasing in associativity in all types of networks. This suggests that the initial network associativity is a good indicator of the robustness of a given network. From the above experiments, we can see that, similar to monoplex networks, associative networks have shown higher robustness against attacks than neutral and disassociative networks. In summary, in this paper, we proposed and demonstrated the effectiveness of a new multiplex network centrality algorithm known as multi-core rank. We show that multi-core rank is a useful centrality measure that accounts for the multi-layer nature of multiplex networks. By analyzing the K-core structure, we've shown that the initial network associativity is a good indicator of the robustness of a given network. As future work, we wish to study defense mechanisms to improve multiplex network robustness. We're now open for questions. Thank you for listening.